So hello everyone. We're gonna present you our project X-ray Vision Solution, which is a tool designed for doctors and radiologists to help them to analyze, classify and localize fractures on X-ray images, human X-ray images. Where does that project come from, since we are both not doctors? It's back in last year where I've developed for my master thesis the same kind of project but for horses. The goal was to design a tool to help them to optimize their workflow, to help them to detect very subtle and how to detect anomalies. The project is still under development and is followed by a few institutions back in Belgium. But for the purpose of this bootcamp, we decided to work with human X-rays. So basically, the pipeline of our work is that first we decided to compare the unsupervised learning method with the supervised learning method that we're gonna tell you more about in a few minutes. Then we did some level extraction with the Google Gemini AI of 30,000 consultation reports from real patients. Then we did convolutional neural networks, which is basically just classifying the images from fractures to non-fractures. And finally, our last model is a model able to highlight the pixels of the X-rays that were very important for the classification. And with that, we were able to retrieve the localization of the anomaly. So the first method we've done is unsupervised learning. So it means that the model learns by itself to differentiate the images from the dataset and to group them into clusters within the same similarities into the clusters. The thing is, our model was very performant, but we noticed that it was more focusing on the biggest similarities in between the images, and we concluded that to be able to go down to the anomaly precision, we would have to do a lot of subclustering. So we decided to go with another more reliable method that Thomas is going to tell you about.
So thank you very much. After we've seen that this unsupervised learning is not really going anywhere because the images are way too complicated, we decided we would go for supervised learning, which the big difference is that you tell the model, this is our outcome. We tell the model you have to learn this by giving it the specific information. And in the unsupervised learning, we're just saying like, oh, do whatever you want to, give us a pattern, and it comes up with a thing. But in our case, our data was actually not really structured in a way that we could use it, because we had 30,000 reports of medical consultations. So this is just sentences over sentences over sentences of things which, to not doctors as we are, not really make sense. So we thought, what can we do to get some kind of useful information, a target for our model for it? And we were thinking, should we hard code it? Should we use some difficult methods in it which take out the commas and the exclamation marks? And then in the end we thought like, oh, everybody's talking about ChatGPT, about these AI tools, and why don't we just use this to feed our model the features extracted from artificial intelligence? And that's what we did with Google Gemini, because thankfully it was for free, whereas ChatGPT costs something these days. And we passed it the prompt, if you go back a slide, where we just told, for all these 30,000 reports, give us the observation, the medical conditions, the body part. And now if you go one further, here in the findings columns we have these reports, and you see it just gives us one beautiful condition that we afterwards could feed our model. So then what did we do? We passed all these X-ray images here of a hand, as you can see, to our model. And what did we get? So then you have to imagine something very complicated, a model which takes all this information and proceeds it, and afterwards it just predicts fractures or non-fractures, because that's the features we in the end were interested in. And as you can see, our model was surprisingly really very efficient. And of the X-rays which presents the fracture, it was able to fetch 88% of these and predict correctly afterwards on pictures it had never seen on X-rays that it was a fracture. And for non-fractured, even better, it was 98%. So if you provided an X-ray which doesn't have a fracture, it will tell you, okay, there's no fracture in it. And this is especially really interesting because our data was extremely unbalanced. We had much more X-rays which didn't have a fracture than X-rays which had a fracture. So it would have been much more worthwhile for the model just to say, oh, it's not a fracture everywhere. And that's a problem we came across a lot of times during our project, that it just was to predict that we always had no fractures. But you can see in the end we got a total accuracy combined with the unbalancedness of the data set of 96%, which is quite good, I would say, in the industry. And so we thought, now that we have that, like you're a doctor, and we pass it to our model, and it just gives you this label: non-fractured, fractured, non-fractured. But look at these pictures, at these images. It's rather hard to see where the fracture actually is in the case there's a fracture. So we just thought, what can we do? And thankfully these days there's something which is called explainable AI, which actually tells you which pixels of the X-ray the model takes to predict whether there's a fracture or not. And thanks to this, the doctor afterwards can just pass the image, and the model looks and returns itself where the fracture is, without having to go nitty-gritty. I mean, here it's rather clear cases, but in general it doesn't have to be, because fractures can be very small. And that's basically all the steps of our model that we have. And so in the end, we have this beautiful demo of our product.
So yeah, so you can see where you drag and drop an images, you click on analyze the image. Then you have you have the prediction, fractured or non-fractured. You have the confidence score. Here it's 100%, so the model is pretty sure that there is a fracture. Then you have a medical AI assistant that will give you a bunch of recommendations about the process, the healing of a fracture. By the way, it's GPT-4, that's Google Gemini. And then we decided to implement the graphical localization. That can take some time sometimes, because it's a very heavy model. But while it's running, we've tried on this model some horses X-rays. Here you can see that the model has correctly predicted the fracture on the right place of the image. And so we've decided to try the accuracy on that model on horses X-rays, and the model has shown very relevant results. Of course, it wasn't 100% correct all the time, but it's not used for horses' bones, but very motivating for the future. So that's a very good baseline for future work. Thank you very much.